Good afternoon, everybody. Welcome to class today. I trust you're having a good week so far. Let's get cracking with today's activities. Let me just adjust this thing. Okay. So I looked briefly at the assignments. Yes, and I see that, or rather, let me correct that. I saw that for those that I looked at, persons seem to have gone through and understood the exercise. Of course, you would know whether or not you're correct because you're really proving that whichever method you use resulted in the same set of parameters or same values for the parameters. So today, I just want to take you along a path of applying these principles that we have learned to normal basic circuit analysis. So let's start with the question on screen. So we have here two networks for which the parameters are given. So we have one network here where we have the Z parameters. We have another one here where we have the T parameters. And then we have some resistors here, okay? So the question is, the 10 ohm load is supplied by a 150 volt source via the network shown in the figure. So we have our load, we have our source. All right. So the question is, determine the power supplied to the load. I know the power consumed dissipated by the load. So given what we have here, I'm going to just go down my list and tag some persons. All right, let me start with, I don't recall having this name as part of my list, but anyway, let's go. Jackson.
Oh, sorry. The person had borrowed by thingy and forgot to sign out. Apologize.
But adjust the name. All right, while you do that, I'll go to Ms. Richards. Let's start with you. How do you want to approach this? You want a full answer? Just tell me how you're going to approach it. Daniel?
Yes, sir. Hello?
Go ahead.
Yeah.
Go ahead. I'm hearing you.
Approach is the 10 ohm load is supplied by the 150.
You're very low though, Ms. Richards. Can you speak up a little?
All right, you hear me now?
Yes, much better.
So I'm just reading the question. The 10 ohm load is supplied by the 150 volt source that is shown in figure 2. So how I would go about approaching it, I would look at the center part first, where the T network is, and go ahead and solve that.
Go ahead and solve it.
Yes.
What do you mean by that? Explain that to me. Assume I know nothing, which possibly could be true, but anyway, assume I don't know anything here. Take me through what you do, why you do it.
Give me a second.
All right, while you're thinking about it, can I have another volunteer? Can I have a volunteer, or do I need to choose somebody else?
Sure.
All right, go ahead, Mr. Marshall.
All right, so me personally, sir, I would find the transmission parameters for the T network in the middle, and then for the Z parameters for network for the Z parameters, I would convert that to the transmission parameters, and then I would multiply all three to get the overall transmission parameter.
Fair enough. And that's what I would have expected. Thank you, Mr. Marshall. All right, so now that we are, is there anybody who disagreed? Is there another approach that you would want to take? Anybody else? All right. So now that we have agreed on now that we have agreed on the method, since there are no dissenting voices.
Sir, how about, he said converting the impedance parameters to transmission parameters, correct?
Yeah, that's what he said.
How about converting the transmission parameters to impedance parameters?
You mean these?
Yes, sir. How about that method instead? As in,
No, if I do that, or if we took that route, how would that then bring me to the final solution?
because you'd have, if you're trying to find power, you already have your voltage source, you'd have your resistances, but with your impedances, you'd have all the resistances necessary, I guess, to find the power. I mean,
Okay. All right. So, you know, I'm going to tell you why you're making that error.
Mm-hmm.
Simply put, you weren't here last week.
Fair enough.
All right. So I will forgive you for making that error. So the point is, and I think this is what this is the only thing Mr. Marshall left out, is that the three networks are connected in cascade. Because they are connected in cascade, then we'd use the transmission parameters for each and multiply them in the order in which the networks are set up. All right? So go ahead for me and convert the Z parameters to T for me. So call this network A, call this section B, and let's call this C. So I want to find TA. Everybody, go ahead. Find TA for me, please. Do you have an answer for me? What's TA? So Thompson?
Oh, sir, I was still calculating, sir.
All right, quickly. What's the formula for Z to T?
Sir, it is Z11 over Z21. Sir, Z to T.
Yeah, Z to T.
Z11 over Z21. Delta Z over Z21.
So you're dividing through by Z21, yes?
Yes, sir.
And you have Z11, delta Z, Z22, and 1.
Yes, sir.
Good. We have to start, we have to be a little more efficient on these things now, students. We can't be spending so much time on this. So we have your 20 over 15, 275 over 15, 1 over 15, and 25 over 15. We okay with that?
Yes, sir.
All right, now let's look at network B, which are those three resistors. Now, you have many options. If you look at, for network B, Just network B. Would you agree that it's symmetrical?
Yes, sir.
Yes, sir. Yes, sir.
All right. So what would be easiest to find? It's a symmetrical network. Which parameters would be easiest to find?
Z11.
Z, the Z parameters.
Z
Yes,
parameter.
sir. Impedance parameter.
Good. So Z here would be equal to what? You have been practicing, you know, so you know this by heart now. What did Z11 be equal to?
30.
30. So if 11 is equal to 30, what is 22?
30.
Huh?
30 as well.
30.
30.
Good. And Z21?
Negative 20.
No, Z, you know, Z.
Oh,
Z21 is V2 over I1. So what would that be equal to? Where would I1 be flowing? If I2 is 0, where would I1 be flowing?
the 10 and 20.
You guys mumbling, I can't hear that.
10 and
The
20.
split 10 and 20.
You're flowing through the 20 ohm resistor, yes?
Yes, sir.
Good. So what's V2? V2 will be 20 I1. Agreed?
Yes, yes, sir.
So what is Z21?
1 over 20, sir.
It can be 1 over 20.
20, sir.
20. So if 2, 1 is 20, then 1, 2 is 20. So we know the conversion in terms of Z to T. So TB, yes, 1, 1 over 2, 1. So that is 30 over 20. Good. It's delta over 2, 1. So that's 500 over 20. And 1 over 2, 1, that will be 1 over 20. And then 2 over 20 over 2, 1 would be 30 over 20. So, I mean, I went rather quickly on this for a particular reason, because one, you need to use the theory that you're familiar with. So quickly, you know about symmetry. So because it is symmetrical, you know that if you're looking at impedance parameters, you only need to calculate 2 of them. So you won't need to calculate all 4. So if you know any 2, you will know the other 2. That's what symmetry gives you. Of course, that would not be the case for your hybrid parameters, but you know that you can get that quickly for your Z. Fair enough? And the same thing is true for your transmission, but you can get it for your Z and your Y. So you get those, you use that to your advantage. So, oops. All right. So we have our TB, and of course we have TC.
Yes,
So
sir.
T would be equal to TA, TB, TC.
Sir,
Yes?
sir, could you show your phone ZB again, sir? And TB. Did you just use the conversion?
Pardon?
Did you convert the T to ZB? TB?
I found ZB and converted it to T.
Oh. Sir, how did you find ZB, sir?
From first principles. All right, so multiply these 3. So you have TC already given. That's 8 over 3, 18, 1 over 6, and 3 over 2. Yes, so you have TC. We have just found TB, and we also calculated TA. So multiply all three from it, please.
Twenty 215 over 12.
I mean, you can use decimals if you so desire. But since you started on the fractions, continue.
Then T12 is 575 over 4.
Huh?
T12 is 575 over 4. And the one is 71 over 60.
71 over?
60. And 191 over 20.
All right. No, I don't think anybody in the group this afternoon should have an issue with quickly multiplying these matrices. I think I have preached enough in networks one that you ensure that you have a good calculator, all right? So, this should not be an issue. You should be just plugging these things in.
Sir, what was the resistance value at the load? I never got it.
10.
10, all right.
All right. So before we so we have these as our transmission parameters for the combined network. So if we just clear this here. So for all of this, the parameters we just calculated, we can now ignore all of that and put in our T parameters, which is a combination of all three. Okay, so we have 150 volts. So with that said, can I have the formula?
V1 equal
And what is V1?
150.
150, sir.
Is equal to
215 over 12.
215 over 12.
Times negative 10 I2.
No, let's not do that yet.
Times V2.
V2
Times V2.
minus 575 over 4 I2.
Next equation.
I1.
equal to 71 over 60 times V2 minus 191 over 20 times I2.
Okay? And now you can make your substitution, Mr. Artist, which is that V2 is equal to
Negative 10 I2.
all right, so this is where we are. Does anyone have any questions regarding what we have done so far? Any questions so far? Okay.
No, sir, you're good.
All right, so I want you now to solve for me. And what are you trying? What value are you trying to get?
I2.
I2.
So you're interested in I2. So calculate I2 for me, please. All right. So what do we get for I2?
Zero
So
point. All right, go ahead.
72 divided by 155. That's it.
All right, give me a decimal now.
0.465.
465.
45. 0 point.
All right, so we can find P. We can find, if we wanted V2, we could find it. If we wanted energy and we give you the time, you can find it. All right. I asked the question for the last time. Does anyone have a difficulty with this? Okay.
Sir,
All right.
Sir, someone is asking a question, sir.
Where?
sir, I've got the answer.
I see no hands raised. I see nothing in the chat. All right. So, figure 5 shows an 8-ohm load being supplied by a voltage source Vs via a 2-port network. If Vs equal 50, determine the output voltage V0 and hence the power dissipated in the load. Given that the hybrid parameters of the network are, and you have those hybrid parameters, and here's your network, okay? So you have, what time is it? You have 15 minutes. All right. Does anyone have a difficulty with this?
Sir, since it's now a T network, does it mean you can still use the same equations to determine the hybrid parameters, sir? Like for H11, we would use V1 over I1 by short circuiting week 2.
No, hold on. Why do you want to do that? What, you're talking about this network? This
Yes,
part
sir.
of the network?
Yes, sir.
Why do you need the hybrid parameters?
Sir, I was considering to use some division to determine the
Planning to use what? Speak up now, Mr. Thompson. Your voice dropping off. I'm not hearing you clearly.
sir. Can you hear me, sir?
Go ahead.
Oh.
Go ahead, Mr. Thompson.
Sir, I'm not sure what is going on, sir. I just wait until you demonstrate it to us.
No, I'm not demonstrating anything.
All right, sir, what I was going to do, I was going to find the hybrid parameters for each network.
For which network?
Find it for A, B,
What
and
is
C.
A?
Sir, A would be what you have circled. The parameters
You see,
that
I
were
have
given.
not given you any network called A, you know.
Oh,
I've just given you a network. So you need to tell me what you're segmenting and then you move from there. So you say you're calling this A.
yes, sir.
What is this?
I would call it B.
All right.
Use the parameters that were given.
So you're using A and B.
Yes, sir.
Okay.
The third
And
one
what are you doing with A?
Sir, I was finding the hybrid parameters.
Okay, fine. And I'm asking you why. What would that get you to a solution?
Sir, after finding it, sir, I could convert it to get the variables that match the first principles equation.
Yeah, but I'm asking you, why are you doing that? What is the objective of the, what are you asked to find?
Sir, the output voltage VO.
Good. So you want this out here?
Yes, sir.
Okay. So I'm asking you now, in finding HA, how does that help in you getting V0?
Sir, using the parameters H, using the H matrix that is given, and assuming that it is for the B network, I was going to try to use to determine the same for the 8 ohms network. So
What about the 8 ohm?
determine the parameters likewise for the 8.
Why?
After doing that, I can use the first principles equation.
And you keep talking about first principles. I don't know what you're referring to by saying that. But before we get to the 8 ohm, you have told me that you're going to find HA, yeah?
Yes.
And I'm asking the question for the 5th time. Why? Why do you want HA? How will HA assist in you finding a solution?
So I assume that after doing that, you could use it to determine the same for the network that is
Okay, Mr. Thompson. We just did a question. I asked whether or not persons understood the principles. You were quiet. But now you're asking me questions which suggests that you have not understood anything we have said from the second class of two-port networks.
No, sir. It's due to this being a T network. I was wondering if you.
But it has nothing to do with it being THQP. It doesn't have anything to do with it. And I repeat, the questions you're asking suggests that you have not understood anything we have said since the second class of two-port networks. There is absolutely no need to find the hybrid parameters. As a matter of fact, all that will do is increase the amount of time you sit in the exam, spinning on wheels. You have the H parameter for the network, as it says here, the parameters for the network. And see the big word here, network. These three resistors, if you consider them a single network, yes, then you could give them a name, A. But this network A and our network here are connected in cascade. So what you're interested in finding are parameters that would describe what I will call C. So let's call that B. So you want parameters for network C, which is a combination of A and B. So TC is equal to TA times TB. You do not need to find Z. You can go straight ahead and find the transmission parameters. All right. A is V1 over V2 with I2 equals 0.
Could you repeat that, sir?
A, V1 over V2 with I2 being 0. So A, V1 over V2 with I2 being equal to 0. If I2 is 0, based on the network you have here, and I'm looking just at the 6, the 9, and the 15. So for this network, you'd have V1, you'd have I1, you have I2, you have V2. All right? So with respect to V2 and V1, from what we have here, V2 would be equal to, what was that, 15?
Yes, sir.
Start with 15 V1 over 15 plus 6. So from that, we get 21 over 15. So A is 21 over 15. Anybody get that? Whether you went Z,
Yes, sir.
or just went straight to T?
Yes, sir. Yes, sir. We got that, sir.
Yes, sir. All right, good. Of course, you can find C, because I2 is also 0 for C. So C is equal to I1 over V2. It's I1 over V2 with I2 being equal to 0. Again, you go back to your circuit. I1 would be passing through the 15 ohm.
Yes, sir.
Yes? So it means therefore that V2 would be equal to 15 I1. So it means that C is equal to 1 over 15. Everybody okay with that?
Yes, sir.
Yes, sir.
Yes, sir.
For D, or rather, not D. For B, we have V1 over minus I2. All right, and this is with V2 equals 0. V2 is equal to 0. What we're saying is that you have a short circuit there, okay? And we want V1 over minus I2. So we have the 6, sorry, it's 9. So we have the 9 and the 15 in parallel. So that is 135 over 24. And then we're going to divide V1 between 6 and 135 over 24, and then multiply that by 15. All right? Oh. Everybody with me? I hope I'm not losing anybody.
Oh, following, sir.
No,
You-
sir, following.
Multiply what by 15, sir?
Ready?
Multiply what by 15, sir? I didn't quite hear that.
Hold on. So let's come back. Let's just do everything. So voltage division, that is between 6 and 135 over 24. All right? So what we want is a relationship between V1 and I2. All right? So we want the voltage across the parallel section. So that would be V1 times 135 over 24 over 6 plus 135 over 24. Uh, 24 times 6, that's 144. Right. 144 plus 135. So we get
279.
279. So we have V1 135 over 24 divided by 279 over 24. All right? So that gives us 135 V1 over 279. And we're dividing that by, what's the impedance? It's 9 ohms. In order to get I2, minus I2.
Sir, it's 8 ohms.
Yes, sir.
Yes, sir. 9 ohms.
Again? Sorry, the rain is pounding.
9 ohms, sir.
So it's 135 over 279, V1 divided by 9. And that should give us 15. So B, I'm getting that to be 15 over 279. Just verify that for me, if it's correct.
Sir, for D, sir. Again.
Wouldn't it flip, sir? Bobby?
What did I say?
Wouldn't it be
Hold on, let me look back. Let me look back. What did I have there? Oh, this is V. This is the voltage across and divide that by 9, we get I2. So just a minute, Mr. Dixon. I think I am rushing. I'm going faster than I need to. So that times V1 is equal to I2 minus I2.
Yes, sir, minus I2.
So it means that V1 over minus I2 is equal to 279 over 15. So that is B.
Yes, sir, that's.
Yeah. All right. With the same circuit, meaning with that short, you're looking for the relationship for D, which is I1 over minus I2. So D is equal to I1 over minus I2. Right? So that will be current division. So minus I2 is equal to 15 I1 over 24. All right, so I1 over minus I2 would be 24 over 15. All right, so you have your parameters. As I said, if you chose to determine the impedance or admittance of these and then convert them, you should get the same values for A, B, C, and D.
Yes, sir.
All right. You have the hybrid parameters for the network. I hope you're able to hear me over the rain. Yes, Mr. Bora.
Yes, sir. Could you go over B for me, sir? I'm getting 31 over 15, sir, so I'm wondering if I did something wrong. Could you go over it again for me, please, sir?
All right, so you agree that this is fine?
Yes, sir.
All right. What we're trying to do is to find the relationship between V1 and I2 with this being short-circuited. So if I short-circuit this, it means that these two will be in parallel.
Yes, sir.
So what I've done is to find the resultant of these two, which would then be in series with that.
Yes, sir.
So the resultant is 135 over 24.
Yes, sir.
I then use voltage division between the 6 and this combined resistance because they are now in series.
Yes, sir.
All right?
I get up to that part, sir, but I guess we're lost.
Yeah, we're continuing. All right. So this is the voltage division. V1 times the resistance you're interested in over the sum.
Yes, sir.
So this gives me 144 plus 135, which gives us 279 over 24. So we can get rid of the 24s. So I get 135 what that. This is equal to the voltage across the parallel section.
Yes, sir.
So I2 would be the current through the 9 ohm. So if I know the voltage across this section, sorry, the current through the 9 ohm would be that voltage divided by 9. which is what we have done. So V1 over minus I2 is 279 over 15, which is B.
All right, sir. I still lost where I get the 279 from, sir, but I'll go by
144 plus 135.
But sir, what I'm saying, sir, is that in the previous slide you have 135 over 279. But when you go on the next slide, sir, I don't say you reduce it, sir. Because when you go on the next slide, sir, you have what? You have 279.
You're okay with this?
Yes, sir, but when you go on the next slide, that's where
I'm
I'm lost.
dividing it by 9. 135 divided by 9 is 15.
They don't divide the denominator, sir, the 279.
So, Mr. Boro, I can't teach you fractions to this, sorry.
All right, sir.
All right. So D is equal to that. So saying you have the hybrid parameters for this network. So you'll find the T. So you convert that, all right? So you have your T network. You find your overall T. Which would be TA times the network. Once you have gotten that, then you put them in the transmission parameter equations and calculate your power for your VO, which is what you wanted, and that VO would be the V2 for the overall network. All right? Based on the questions I've gotten today, for example, what I just went through with Mr. Boro, that has nothing to do with two-port networks. So there's nothing I can add from a two-port networks standpoint to deal with that. With respect to what Mr. Thompson had asked, Mr. Thompson, you need to look back at your notes. You need to review the videos and take it from there. And so we're going to call it a day for two-port networks. I'm therefore going to move right away into the next topic, which is circuit transients. So let us start. It's now 11 minutes after 2. Okay. So let us start with some basic definitions as it relates to the transients. All right? Unlike any other topic that I have taught, it's important that we pay attention to the simple things, even if we are very familiar with them. I encourage students just to, humor me, and pay attention to the basic definitions. All right? So I want to talk about circuit transients. Get some definitions out of the way. And that first statement I made about, humoring me and doing what, and us following the simple things, getting the definitions clear. Mr. Ford, I think, says it better than me. Sometimes we run the risk of thinking we already know or understand the topic based on experience, but, at times just need to stop and try and relearn those things that we may be very familiar with you know, respect it enough to try and relearn. You may just find a nugget or two that you had overlooked in high school or elsewhere. So let us try and remain young, eh? So by definition, when a circuit is switched or when we make changes in a circuit, so whether it is you're at home and you turn on the light, or you turn the light off, or you turn on the radio, you name it. So when you change the state from one condition to another, either by applying a source, which will be like turning on the radio or turning on a light at home, or you change a circuit element. So you might have the circuit in operation and you opt to remove a component. May not be the wisest thing, but hey, it can happen. So we can switch between components. Eh? There is that period during which the branch currents and the voltages will change from their former values to new ones. Now, students, the reality is you will not necessarily be able to detect the changes that are taking place. One thing you know is that when you turn the light on, the place becomes a little brighter, at least hopefully. One thing you know is that when you push the power button, the radio come on, television come on. You are not there seeing what is happening in the background, but these changes occur. So you have currents changing, you have voltages changing. And this period, the period between which you initiate a change and it reaching what we call steady state, is known as the transient. So that's the simple definition for a transient. When we make a change in a circuit, whether we add a source, we remove a source, add an element, remove an element, currents and voltages are going to change. And the period between the initiation and where it settles is known as the transient. Now, after the transient has passed, that is what we call steady state. So in terms of definitions, and as far as transients are concerned, I am done. I have nothing further to say. However, I will link this whole business of transients, I will link it to a couple of things that you have done in math. All right? Can I move on?
Perfect.
If we are able to write a differential equation, and that differential equation describes the circuit current or voltage, yes? So I first of all develop a differential equation which tells me what the relationships would be between the current and the voltage. In solving that differential equation, when we solve the equation, it will have two parts. We have the complementary function and we have the particular solution. I know this is not strange to you, but hey, just work with it. So you have the complementary function and you have the particular solution. For our purposes, the complementary function of the solution describes the transient, while the particular solution describes the steady state. So our task is to first, based on the elements within the circuit, our task is to derive or determine the differential equation. And once we have found that differential equation, when we solve it, we'll get the transient and we'll know what the steady state will be. So, using what I believe you're familiar with, yes? We're just gonna go back to some stuff that you would have done, you have already done in physics, but we'll now apply some networks principles to it and see where we go from there. So let's get started. So let's talk about your RC transients. So here's our circuit. All right, so couple of things that we need to take note of. One, we are told that the capacitor has an initial charge Q0, which corresponds to an initial voltage V0. Of course, we know that Q equals CV. Yeah? So the initial charge Q0 corresponding to initial voltage of V0. Now, the things that we would have introduced here is that we see here T equals 0 plus. Question is what that means. So that's one of the things we are going to introduce in transients. So we have 3 zeros that we are going to talk about. We have 0 plus, we have 0 minus, and we have 0. So you have 0 plus, as shown there. We have 0 minus, and we have 0. Now it is very difficult to do our analysis at 0. Yes? So usually we talk about 0 plus and 0 minus. What's the difference between 0 plus and 0 minus? Simply put, 0 plus means immediately after closing. So 0 plus speaks to immediately after closing. 0 minus, therefore, means immediately before closing. All right? So just before we close, the other one just after we close. All right? So nothing too fancy. The other thing we want to take note of is that the energy, we're going to come back to this later on, but just take note of it. The energy is equal to half CV0 squared. Yes, and if we substitute for V0, yes, that would give us a half Q0 squared over C. All right? So the energy contained in the electrostatic field of the capacitor is given by half CV0 squared. Okay? All right. So we have established all of that. So at the time T0, when, as I said, when the switch is closed, immediately after the switch closes, we would expect that charge would leave the capacitor, yes, and the stored energy falls to 0 via the conducting path through the resistor R. That's what we expect. So in other words, our capacitor here would be like a source. Let me withdraw that. Our capacitor here is a source because it has stored energy. All right? And once we close the switch, immediately after we close the switch, we are going to find current leaving that and heading through our resistor. All right? Now, of course, based on the polarities that I have, we would have expected the current to be going that direction. Yes? And so we'd have plus minus here. But just work with me for now, you know. I am telling you the current going in the opposite direction. If it's wrong, our math will prove it. If it's right, our math will prove it. So I have nothing to lose. So closing the switch, the charge leaves the capacitor and flows through the resistor. Yes? And the energy that would be stored will go to zero. So based on the circuit we have, if we consider the Kirchhoff's voltage law, we have a closed loop, because once we close that switch, we have a closed loop. So it means that VC plus VR equals zero. And based on the diagram that I have here, whatever the voltage is across here, plus that voltage will be equal to zero, because we have no other source in the circuit. So those voltage drops equals zero. Of course, VC, and note I'm using lowercase c, which means that it's instantaneous voltage. So the voltage across the capacitor at any point, plus the voltage across the resistor at that same time, would be equal to zero. Again, we're using lowercase q, which again speaks to the charge at a point in time. So it's an instantaneous charge that we're looking at. That instantaneous charge at the same time, t, would give us VC. However, for VR, yes, dq dt would be equal to lowercase I. So the current in the circuit, yes, is a rate of charge or rate of change of charge. And that is how we define current. Agreed? I'm not saying anything strange, am I? So we have VC plus VR equals zero. Q over C plus R dq dt is equal to zero. Of course, we just spoke about dq dt. Yes. If we divide through by R, we get dq dt plus 1 over RQ, 1 over RC times Q is equal to zero. And what we have here is a simple first order linear differential equation. And we know that Q, as we have said before, is equal to CV. And it's important, students, when we're dealing with transients, that we distinguish between instantaneous and steady state values. So instantaneous, we use the lowercase. So once you see us using lowercase, you know it's an instantaneous value. When we use uppercase value, you know it's a final value, all right, or an initial value. Okay? All righty then. So Q equals CV, and remember now, what I'm interested in, or what we're interested in, is finding the voltage across the capacitor at any point in time. So making the substitution, the variable here would be V, yes, because the capacitance is fixed. So we have C dV dt plus VR, V over R, Remember we made this substitution? We're making that substitution up here. All right? So C dV dt plus V over R equals 0. Making the coefficient of the differential 1 of dV dt and if we use separation of variables, we have dV over dV dt equal minus 1 over CR. And continuing along this path, which is a path that you're quite familiar with, we have dV over V equal minus dt over CR. All right. And so if we integrate we're integrating f prime over f. So we know that that would be ln f. So the first differential over the function, the integral of that would be ln. Plus k. All right. So our next task is to determine K. Now, up to this point, everything that I have done is what your math teacher would have done. I have not changed anything. But your math teacher would then give you the boundary conditions. So they would say, you know, at t equals 0, this is what is the case, and at, you know, t equal infinity or d, all of that fanciness. Those are the boundary conditions. The challenge students in transients, the challenge for you is that you need to then look at the circuit and determine what those boundary conditions are. So no one will now tell you what the boundary conditions are. By virtue of the circuit elements and the conditions that we indicated, you must be able to say what these boundary conditions are. So in finding K, we look at the initial conditions. What are the initial conditions? At t equals 0, what do we know about the voltage across the capacitor? Anybody? At t equals 0.
It would be still fully charged, sir.
So what's the voltage across the capacitor?
VC.
0.
Think about it. At t equals 0.
VMAX.
Huh? So Dixon, what was that?
I was saying VMAX, sir.
Did we ever say anything about Vmax? So Dixon, come on, talk to me.
No, sir.
What did we talk about?
To be equal to VC, sir.
V0.
Yeah,
Don't put the V max. We have not mentioned that. So it's V0. We don't know if the capacitor was fully charged. So we can't be talking about V0. What we know is that it had an initial charge of Q0. Doesn't mean that that was the maximum. You with me, Mr. Dixon?
yes, sir. I agree, sir.
All right. So at T equals 0, we know that the voltage across the capacitor is 0. So we are going to therefore make the substitution in our differential equation or in our solution. Yep. So let's clear that. So at T equals 0, we know that the voltage across the capacitor is V0. And so we make the substitution and we get K to be equal to ln V0. This is what we are substituting in at T equals 0. What is this? So V here would be equal to V0. So that's the substitution we are making. So it means that K would be ln V0. And since we are all brilliant math students, if K is ln V0, right? We bring that to the left-hand side. We, of course, get ln V minus ln V0. Or, since we are subtracting logs, then it means that we are dividing. And what we want is V. So if we have ln V, yes, and what we want is V over V0, then what's the reverse of ln?
Exponential.
Exponential. So it means that Vt is equal to VOE to the minus T over CR. Now, this is a formula, as I said, I am doing something that you are familiar with. This is a formula. The fact that you are sitting in this class, it means that you would have seen this formula before. All right?
Yes, so that would be the formula for discharging a capacitor. The amount of, yeah, basically along those lines, sir. Like the amount of voltage that will be left after a certain period of time of discharging the capacitor.
All right, that's a lot of information. You are correct. And we call it, in the simple name we give to this is the Helmholtz equation, capacitor discharge. All right, and this is something that you would have seen from fourth form. Okay. If the initial is just information, so when you see it later on, you can reference it. If the initial time is sometime t equal t0 rather than 0. So in other words, if we start looking at the voltage beyond a certain point in time, instead of looking at it at the point we close the switch. You understand that? So if it's at, if we close the switch and then we start looking at the change in voltage at t0 seconds after, then we would use that.
Sir, could you please restate why would we use that? Just
Go again?
yes, I was asking, could you please restate what you said about why we would use this equation?
It's right here. So we say if we start looking at T equal T0 rather than T equals 0. So if you are looking at the voltage starting at a time T0 seconds after closing. Because remember, we looked at it at 0 plus. And we said 0 plus was immediately after closing, eh?
Yes, sir.
Yes, sir.
If you're looking at it at T0, then this is the formula you would use. All right. Class a little intense today, eh? Don't worry. It will only get better. All right. If we want the current, remember I showed you the current, eh? If I know the voltage across the resistor, I would be able to find the current at all times. So if I can find an expression for the resistor voltage, I have the resistance, so I can find the current. But we know that VR plus VC was equal to 0, as we showed earlier. So it means that VR is equal to minus VC. So VR is equal to minus V0 e to the minus TR, T over CR. All right? So I is equal to minus VO over R. What this is telling us is that the direction is opposite to what we had established or what we had shown. Remember I mentioned that earlier, huh? So in terms of, can I move on?
Just a
Give me a
moment.
minute.
All right.
Okay, so graphically, if we look at the initial charge on the capacitor, yes, being Q0, as time passes, our capacitor discharges until the charge across its plates, or on its plate, sorry, would be 0. Before you draw this, let's just go back to the voltage equation. All right. So here's my voltage equation. We have to test to see if what we have done is correct. Eh? So if I substituted 0 for T in this equation, what would the voltage across the capacitor be equal to? At T equals 0.
V naught.
V naught. Yes. And if T is infinity, what would V be equal to? Lowercase v be equal to?
I don't remember what is e raised to the infinity, sir.
You don't have to know. You don't have to remember. What is 1, or what is 5 to the minus infinity?
Infinity.
What is 5 to the minus infinity?
Wouldn't it be, wait on. Negative.
Oh.
Oh, we would be getting closer to 0, sir. Wouldn't it be getting closer to 0?
Closer to 0.
With a 10 to 0.
Yeah, man.
Asymptotic.
Yes, Mr. Johnson, what's that?
It's an asymptote, so as it goes to infinity, the other one would tend to 0. That's what.
Well, you don't even have to look at the figure. What I want you to do is to look at the equation. And I'm asking you, what is 5 to the minus infinity?
So it'll be extremely close to 0. So it'll be gravitating
Oh, no,
towards
extremely close to 0, Mr. Stewart. Let me pull it through the computer. Let me about extremely close to 0. What is 5 to the minus infinity?
0.
0. So at t equals 0, Vt is equal to V0 as t tends towards infinity. Note, I didn't say 10 towards infinity, Mr. Stewart. I said that e to the minus infinity. Yes?
Yes.
At 0.
0.
So as the time extends, then it means that this goes to 0. If we look at the current expression, yes, again, at t equals 0, what's the current? Substitute 0 here for me, folks. What's e to the 0?
1.
1. So what is I?
negative V naught over R.
Thank you. Similarly, as t tends towards infinity, what is I?
0.
0. So it tends to 0. So in terms of the practical operation of the circuit, it must hold true for the equations that we have derived. You with me? So if you have a charged capacitor and you discharge it across a resistor, what we expect is that the voltage across the capacitor will diminish, the current through the circuit, because you're going to have current flowing, because the capacitor is discharging. The current through the circuit will start at a maximum, but then it will go down to 0. All right? So the graphs should make a lot more sense now. So this is for Q. All right. We have for the voltages across the capacitor and the resistor, which we expect to be the case. They must be equal and opposite, because whatever is across the capacitor will be across the resistor. Okay, they are connected across each other. So we expect that. So for the voltages, that's what we have. While we're drawing this, I think I will use the opportunity to take the register. All right, who do we have here? Atkinson, Beckford.
Beckford here, sir.
Okay. Bigger stuff. Black.
Yes, sir.
So Atkinson was here earlier, I'm sure.
I'm still
Black
here.
coat. Yeah?
I'm still here.
Don't answer your names, huh?
Oh, probably my signal dropped.
Okay. Blackwood,
Yes, sir.
Bora. Bora,
Here, sir.
Brown, Imani,
Here, sir.
Brian,
Yes, sir.
Cameron,
Here, sir.
Campbell,
Here, sir.
Colhoun,
Here, sir.
Dixon, CSC, yes. Gail,
Yes, sir.
Gordon, Romain, all right, Gray,
Yes, sir.
Hanson.
Here, sir.
All right. So these are for the voltages, and then
My name.
everybody have this? I'm just pausing for a moment. Everybody have this?
Yes, sir.
All right. And that's for your current. So your current is minus V0 over R. Okay. Hins, Javon, or Javon.
Javon, sir. I'm here.
Hodges. Yes, Humphrey. Johnson, Kimarley. Jones, Akil. Wait, what happened to that?
Here, sir.
Luton.
Here, sir.
Marsh. So Marsh has been missing quite a few classes anyway. Marshall.
Here, sir.
Matt Bean.
Here, sir.
McCleary. Jamal. McFarlane, Vaughn. McKinnon.
Here, sir.
Morgan. Linval. Morrison.
Here, sir.
Morrison.
Here, sir.
Parker.
Yes, sir.
Peru. All right. So we have this.
Excuse me, sir. Did you call Watson a while ago?
We're not there. We're not there yet. I'm not finished as yet. I'm still at Peru. So let's come back to the notes quickly. So I'll call while they're writing. So given the conservation of energy, the energy stored by the capacitor must be dissipated in the resistor, given the lump parameter circuit model. So what we are saying here is that whatever energy is lost by the capacitor must be absorbed by the resistor. So none is absorbed by the connecting wires, which we know is not true, but hey, it makes life easy. All right? So that being the case, the instantaneous power absorbed by the resistor. So again, we're dealing with some lowercase things. So the power absorbed by the resistor will be given by the instantaneous voltage squared over R. We know the expression for the voltage. We just showed it earlier, which is VO squared e to the minus 2t over CR. And please note, the negative would not be there because we're squaring it. So the negative would disappear. By definition, the energy to infinity is the integral of the power with respect to time. So from 0 to infinity, which is the time period over which we would be looking at the power dissipated by the resistor. So the integral of that power with respect to time, yes, gives us the energy. All right, we have 2 minutes to wrap this. Can I move on? So that's the integral. Let's just finish with the resistor. Powell, William? All right, Ms. Richards is here. Joel Richards?
Yes, sir.
Romaine Richards?
Here.
Sawyers?
Yes, sir.
Stevenson? Stevenson? All right, Stuart is here. Swiby? Swiby?
Sir, he said his tablet started giving issues.
That's Swiby?
Yes, sir. He said his tablet knocked him out of class and he can't get back on, but he was here.
Watson, Michael?
Yes, sir.
Patrick Williams and Travis Williams?
Yes, sir.
All right, so Patrick isn't around. Okay. See if this changes, and that's that.
Sir, go back to your previous page, please.
So this is it for today. All
Back to
right.
your previous page, sir.
Pardon me?
Okay. We'd ask if we go back to the previous page.
So in terms of the integral, so we're integrating the power. So this is the power expression that we had just now. And if we integrate, yes, and make our substitution, we will find that the energy consumed by the resistor would be equal to half CV0 squared. What this is saying to us is that the energy that the resistor absorbs is equal to the energy which we showed earlier. I mean, I just gave you the formula for the energy supplied by the capacitor. So if that supplied by the capacitor is equal to that being absorbed by the resistor, then the law of conservation of energy is obeyed, and we know we're good. All right? So that's it for me for now. I really do not want to, because I realize that very few persons are turning up on the Thursday evening class or to the Thursday evening class.
Sir.
Yes. Yeah.
Sir, when you have that Thursday evening class, I'm in another class as well.
All right. No problem.
So the class is that's okay. Make it to the Thursday class, sir.
Sir,
Yeah.
I have a clash, like I didn't want to go through the whole ad-drop thing, which is why I had spoken to you before about the Thursday. So I spoke to the other person and kind of switch it around because I thought that we were going to continue for 3 hours on a Wednesday.
Okay. Well, I don't have all right. So how many persons are able to stay? No, let me ask the easier question. Just put up your hand if you have to leave.
Sir, put up your hand if what?
If you have to leave now.
Oh, sir, if you have the session today, will you still have the Thursday session?
Just answer the question I'm asking, man, and make a move on. Just answer the question I ask. If you have to leave now, just put up your hands, please. All right, so we have 11 persons that need to leave because you have other classes, and that I will respect. So these are why are the numbers fluctuating? Folks, put up your hand and keep it up. Good. So we have 11 persons who need to go. All right? Fair enough. All right, so we'll continue. Okay, those who have to go, I assume that your class will be tomorrow. All right, fair enough. So those 12 persons can go ahead. We'll just continue with what we're doing now. So you can lower your hands and exit. All right. Okay, so we will proceed for a few more minutes, and then we publish the recording for them and see where we go from there. So I want to continue by talking about RC time constants. Yeah? So here we have a circuit, and we already have established our voltage, or instantaneous voltage. And VO we know is the voltage at time t equal 0. So what? Everybody have this? Okay. So what we have here, we'll draw this for me, and then we talk a little about it.
Can go ahead.
Okay. Okay, so what we have here, we're showing 3 decay curves. We're showing it for RC equal K, RC equal 2K, RC equal 3K. Yes? And we have here a value of 36, well, 0.368 V0. V0, of course, being the initial value. All right. So I'm going to give you now some statements. I'm going to give you 3 statements about these 3 curves that we have. But before I go there, there's a definition that we give to time constant, which is a little more complex than just saying, time constant equal RC. And I'll come back to that in describing these curves, okay? But these are the 3 statements I want to make regarding these curves. First one, the smaller the RC product, the more rapidly the exponential function decreases. All right? So the smaller the RC product, the more rapidly the exponential function Vt decreases. So that's the first statement. The next statement, and bear in mind that we were looking at this value here, eh? This is more of a clarification or being more specific on the first point. And that is the voltage for the RC circuit decays to a specific value in half the time of that required for 2K and a third for 3K. So in other words, that K value for RC equal K, whatever it works out, whatever value that has, if I were to double K, then that would cause the time to be also doubled. So in other words, at K, it would have done so in half the time. If I triple K, it means that the actual time it would take would be 3 times, or in other words, the original K would be a third. Simply put, the higher the RC value, the longer it will take for the voltage to, or for the charge to reach that magical number that we have there. And then finally, the other point we want to make is that while maintaining the RC product, so if we maintain the RC product, it will cause the voltage signal to remain the same. The current response, however, will change because current is given by V0 over R. All right, so let's explain this one. Let's explain it a little further. Let's go back to our equation. That's my equation, yes? By the way, did you finish writing off this? I'm sorry, didn't ask. You finished writing?
Yes, sir.
All right. What we're saying, if I am able to maintain the RC product or the CR product, so when I multiply R by C, if I'm able to maintain the value. So if I have C to be 10 and R to be 5, when I multiply that, that will give me 50. Agreed? But 50 is also equal to 25 by 2. I still get 50. This is C, this is R. 50 is also equal to 50 times 1. Simple point we're making. The R values are changing. The RC values would not change. So it means that this curve would remain the same. Because remember, V0 is not changing. So the curve itself would remain the same, wouldn't change. However, because I is equal to V over R, the current value would change, but the curve would not change. So where it starts would change. So the maximum I, or the initial I, would be different, but the curve itself would not change. Is that clear? Or is it as clear as mud?
As mud, sir.
Good.
And not so clear.
Let's get some water and wash it off. All right? Now, by definition, when we talk about your RC time constant, what we say is that the time required for the response to decay by a factor of 1 over E. Now you can flip out the calculator and determine 1 over E. What is 1 over E? Come on, folks.
E to the minus 1.
Huh? What's that, Mr. Black? 1 over E. What's the value of 1 over E?
0.3679.
Good. Look kind of familiar?
Yes, sir.
All right. So the definition is that the time required for the response to decay by a factor of 1 over E, which is 0.368, is defined as the time constant of a circuit. That's nice and simple. And it is denoted by tau. So Vt equal V0 e to the minus t minus tau over RC. This is now the factor. Because remember we said that it is reduced by a factor of 1 over E. But 1 over E is e to the minus 1. All right? Can we see do we see how we move from here to here? We would have V0 e to the minus 1, yes? E to the minus t over CR. But e to the minus 1 can be written as CRC over RC. You see that now? So RC over RC, that's minus 1. And you still have your T over RC. All right. It's math. Okay. So tau, where tau is equal to RC. So start We finished with this? So let's start about this, and then we do a simple problem to try and highlight what we said earlier with respect to the changing values of RC or maintaining.
Can you go back quickly? Sorry, before you finish. Okay, sir, thanks.
All right, now, this is we have just spoken about the time taken for the voltage or the charge to be reduced by a factor of 1/E. Now, the more classic definition for time constant, I don't have it written on this, so you're just going to have to write it as I say it. All right, so your time constant is the time taken, so your time constant is the time taken for complete discharge So it's the time taken for complete discharge to occur if maintained at the same rate at any point. That I know on the surface don't make any sense. So it's the time taken for complete discharge if maintained at the same rate at any point on the discharge curve. So let's see what that means. If we choose a point on this discharge curve, any point. So if I was to choose, let's say that point. Right? By definition, if I am saying that the charge is maintained at the same rate, how would I show that graphically? So if the discharge rate is maintained at the same rate at any point, how would I reflect that graphically?
Sir, by the so it would be by the curve, like it'd be similar to like a tangent to a straight line, but in a
all right. You see, one of the things I want from you students is to speak with a little more authority. I don't want to little like and right, Mr. Stewart? This is math. Math is precise. So it's not anything like anything. If it's going to be maintained at the same rate, it simply means that it's a tangent at that point. Simple. Okay, sir?
Yes, sir.
Speak with confidence. You can't be afraid if you're going to people's generating plants saying that you want to be engineer. You can't go into people's manufacturing facility and be timid. You have to be bold with the knowledge. These are things you have done in math. That is why we have them as prerequisites. So if we put the tangent at this point, oops. My finger not doing a good job at all. Right? What we are saying is that if you measure from here, at that point, to here, then it would be equal from there to there. Obviously, this is not drawn to scale, so, right? If you took a tangent at another point, let me remove all of this. If you took another tangent at this point, I will mark the tangent there. We're saying that that would be equal to tau. So let me put one in blue so that we can, and again, it's not drawn to scale. So at that tangent, I'm going at the same rate. So if I mark the tangent there, we're saying that and that is tau. And you would agree, even though it's not drawn to scale, that they look almost equal, don't they?
Yes, sir.
So that's the classic definition for time constant. It's time taken for complete discharge. If the charge at any point in time, if the discharge rate at any point on the discharge curve is maintained. All right, so just to wrap today, here are the two questions. So, here is what we have now. Determine the resistor value in a series RC circuit that would allow the capacitor voltage of a 1 microfarad capacitor to be halved every 10 milliseconds. Any suggestions?
Do you want the answer or do you want the process first, sir?
All right, tell me.
Okay, so by using the equation VT is equal to V naught times E raised to the negative T over RC, because it said that the voltage would be halved, so therefore VT in this case would be V naught over 2. So I replace VT with V naught over 2, and then I have V naught times E raised to the negative 10 milliseconds over R and the C value, which is 1 microfarad. I converted it from exponential form to ln form to give me a half is equal to, ln a half is equal to negative 10,000 over R. I transpose
10,000, 10 milli, 10 milli, not 10,000. 10 milli. You said 10,000 just now.
No, it's because I did. It's because I already calculated it 10 milliseconds divided by 1 microfarad. That's what.
Oh, okay. So it's 10,000 R. Okay.
Yeah, 10,000 over R.
Okay.
So when I transpose, I got 14.427 kilo ohms.
Anybody else got that? Did anybody else get that?
Yeah, how much? What was that?
14.43 kilo ohms. Did anybody else get anything like that?
Yes, sir.
Well, 14.427.
Yes, sir.
Okay. Ms. Campbell, what you got? Are you waiting on me? Let's Campbell disappear. So McFarlane? Wait, what is that? What is that?
You hear me, sir?
Yeah, man, go ahead. Go ahead, Mr.
I use a different formula, sir. I didn't get that. I only get 10,000. I get 10 kilos by using equal R.
All right. Okay. Okay, listen. So it says that it's halved every 10 milliseconds. So it means you're using, as Mr. Stewart said, VC is equal to V0 e to the minus t over CR. If it's halved, it means that VC would be equal to V0 over 2. That's equal to V0 e to the minus t over CR. So a half then is equal to e to the minus t over CR. You have t, which is 10 milliseconds. You have c, which is 1 microfarad, and you are to find r. So from this, r is equal to 14.43 kiloohms. All right, I'm not gonna do the math for you. For the second question, we have a series RC circuit. It has a 50K resistor and a 0.02 microfarad capacitor. We want to increase the current in the network by a factor of 5 without changing the capacitor voltage. So if I'm going to increase the current by a factor of 5, yes? If I'm to increase the current by a factor of 5, Cameron, what do I do if I need to increase the current? Cameron. Cameron isn't here? Folks, you know,
Sir,
right?
you have to,
Hold on, Mr. Colon. I said Cameron. And if Cameron isn't here, then I will just help him or her. So, you know, we won't waste any time. We're done with this foolishness now. Yes, Mr. Colon, go ahead.
I would assume that if the current is I, you would have said I plus I over 5.
If I'm to increase it by a factor, what factor mean, Mr. Colon?
A fraction of what the current is.
All right, fraction, you say? If the current is 2 amperes and I'm increasing it by a factor of 5, what would the current be equal to?
2 over 5.
All right, then. That's not true. That's not correct. I was trying to find another way to try and explain it. But if you increase something by a factor of 5, it means that you have multiplied it by 5, Mr. Colwood. So if it was 2 amperes and you increase it by a factor of 5, it is now 10. So
okay, yes, that was what I had in my mind first. Sorry, sir.
Yeah, well, your mind and your mouth need to be connected, all right? Ms. Richards?
Yes, sir.
Based on the question, if I am to increase the current by a factor of 5, what would I need to adjust?
The resistor.
The resistance. So the resistance would be reduced by a factor of 5, no?
Yes, sir.
Beautiful. So you have the resistance, which is 50K. So what's the new resistance value that you would use?
10K.
10K. Now, in order for the voltage across the capacitor to be maintained, what needs to remain the same? Ms. Richards?
The resistor times capacitor, that RC thing.
Beautiful. Wow. There was somebody actually listening. Thank you, Ms. Richards. You have made my afternoon. I'm serious. I'm serious. So if we reduce the resistor to 10K, yes, how would I then what would be the value of the capacitor?
The original value times 5.
Which is? I can't do maths.
0.1 microfarad.
Huh?
0.1 microfarads.
All right. Or give me another subunit for that. 0.1 microfarad or? Come folks, you're in electrical engineering. Come, give me a subunit.
100 nanofarads.
Thank you. So it's 100 nanofarads. And that's it. All right, folks, you had quite an introduction today. I know it was a little heavy. It's a lot, but I would strongly encourage you, if you are going to, in order to keep up next week when we meet, it's absolutely important that you review what we have done today, because we are going to take it to another level next Wednesday. All right. I know it's a little difficult, 3 hours of networks. I mean, even I am tired. So I can only imagine what you're going through. Okay, so that's it for me for today. You have a good one.
Yes, sir. Yes, sir.
All right.
Take care, sir.
All right. Bye.